Hey everyone, the next problem-solving pattern we'll talk about, I'm calling multiple pointers. Again, it's not really an official name for it, but let me just read the definition first. The idea is that we create pointers or values that correspond to an index or position, and then move towards the beginning, towards the end, or towards each other in the middle, based on a certain condition. Okay, so what it really comes down to, we have some sort of structure, linear structure, like an array, or a string, or later on, we'll talk about things like a doubly linked list, which you may not be familiar with, or even a singly linked list. If you don't know what those are, don't worry. And the idea is that we're going to be, searching for a pair of values or searching for something that meets a condition. Usually we're looking for a pair, and I'll show you an example in a moment. And we use two references. So we start one reference maybe here and another one here, and we work towards the middle, towards each other. Or we could start something here and another, like when I say reference, I mean a variable like I and J, which are numbers referring to indices. So we could start I here and J here, and then we move them forward in a certain way. So there's not, a guaranteed direction. This is sort of a loosely defined one compared to what we saw in the last video, or the last sort of pattern, frequency counting. But this does come up pretty often. I'll show you a couple examples. So just to recap, we have a pointer, which is just a variable. We're looking at a specific location in an array or a string usually. And then we have a second one, and we work towards each other, or we work in the same direction. We work from the end towards the beginning. It doesn't matter, but we use two pointers. So let's talk about an example where this could make sense. An example. Okay, so write a function called sum0, which accepts a sorted array of integers. So it needs to be sorted, not assorted, but in order, sorted from lowest to highest. The function should find the first pair where the sum is 0. So the first pair where you take one number and you add it to another number and it's equal to 0. So you can see here, -3. First of all, this is a sorted array, -3 up to +3. And in this case, -3 plus 3 gives us 0. So we return that pair in an array. Otherwise, like in this case, there is no pair that sums to 0. So we return undefined. Same thing here. So how would you approach this? First of all, it's important to note, and remember I'm hitting this a lot, but it is sorted. If it was unsorted, then we're kind of out of luck as far as coming up with an efficient solution. But it is sorted, and we're looking for something that sums to 0. So we know that we have small numbers here, and the largest numbers are up here. And because of that, we can use two pointers and test for sort of certain conditions to see if we want to move down or want to move our other pointer up. But first, let me show you the naive solution. This is the simpler one that has time complexity of O of n squared, it's quadratic time. And you can see right off the bat, we have two loops. We're using one for loop and a second for loop. So what this one does is it starts a pointer looking at -3, and then we have a second loop that iterates over the entire rest of the array, the entire rest of the string, the structure, looking for something that adds to -3 and equals 0. So looking for 3. So we go all the way through and we happen to find a 3. And so that's a simple example. But imagine that there wasn't a 3 here. Then we would move on to -2 and look through the entire array to find a -2. And if we're talking about a 10,000 item array, that's a lot of iteration when we have these nested loops. But this is the simplest way. You start here, and then you compare it to every single other number. And then if there's no match that equals 0, you move forward 1 and compare it to every other number and keep going. So here's the example, the naive version. It does work if I run this. So we've got -4, -3, and so on. We would start here. We look for a match. There is no 4. So then we move to -3. There is no match. We compare all of these different things. We get to -2, and we compare it to every single other item until we hit 2, and we found a match. So even in this case, we had to do a bunch of operations to figure out there was no match for -4. Then we go to -3, and we have to do a bunch of operations. And this is a small array. So this could benefit from a refactor using the multiple pointers pattern. So here's how it would work. We would start a pointer here and start another one up here, because we know that this is the smallest number and this is the largest number. And we start by just seeing what the sum is. What do they add to? Well, -4 plus 5, that's going to give us a positive number, which is 1. And that's too big. We're looking for 0. So 1 is greater than 0. That's not what we want. So what we would do then is move this pointer down to 2, because this is the smallest number we're going to get. So maybe, just maybe, there's a 4 here, but there's not. But our code doesn't know that, so it's going to look one below and hope that now we're going to sum to 0. So we add -4 and 2. Well, this time it's too small because that's -2, and that's less than 0. So that means we're going to add 1 to the left side because there's no match for -4. Remember, it's a sorted array. So we go up. Now we're looking at -3 and 2. Well, we add them together. It's still -1. Well, it's not still -1. It's still negative. It's -1, which is less than 0. So what that means is that we're going to try and add 1 to the left side, which gives us -2. And now we add -2 and 2, and we get 0. And that is the first pair, and we return -2, 2. So way fewer operations compared to using a nested loop and starting here, looking at every single other number, then moving to here, looking at every other number. And this is a simple example where we find it relatively quickly because there's only, 7-ish numbers? I didn't count them. Is it 8? Okay, it is 8. So it's really small compared to 10,000 items, where it would save us a lot of time. So here is that refactored solution where we have 2 pointers, one starting at the left, index of 0, and the other starting at the last index in the array, array.length -1. And I'll take you over to the code in just a moment, but you can see time complexity is linear. It's O of n, much better than O of n squared. So here's the refactored version. And we've got left set to 0, right set to array.length -1. So left is going to be this index 0, right is this index over here. This is a slightly different array. I put 10 in here, and it looks like our first pair should be -3, 3. Okay, so we start and we check the sum of array of left and array of right. So -4 and 10, that's going to give us 6. And we check first, is it 0? Because then we're done. No, it's not. So if sum is greater than 0, which it is, we're going to subtract 1 from right. So right was this index, which I'm not going to count what position, but we subtract 1. So now we're looking at this place, 3. And we're adding 3 to -4. So we start the loop again because nothing else happens. We have an if, an else if, and an else. So only one of those is going to run. So we subtracted 1 from right, moving it down to here, and start over. So now sum is equal to -4 and 3, which is -1 now. So this time it's not 0, it's not greater than 0, so this else runs, which means we add 1 to our left. So now left moves up to -3. Next time through, we sum -3 and 3, which gives us 0, and we're done. If sum is 0, return array of left, comma, array of right as an array, a new array. And just to prove that it works, there we go, -3, 3. And if we give it something that doesn't have a pair, like let's remove that 3 and change this to be a 5. There's no pair here, right? Oh no, we have 1 and -1. Remove the 1. Okay, there should be no pair now, and we get undefined, which is how it's supposed to work. So we stop because our while loop runs while left is less than right. So if they cross over at some point, that means that we've exhausted every possible pair. We tried here and here, that didn't work. That was too large, so we subtracted 1 from right. We tried 5 and -4. Still too large, so we went to 0 and -4. Too small, so we went to -3 and 0. Too small, so we went to -2 and 0. Too small, went to -1 and 0. Too small, so then we went 0 and 0. And we have to stop before there. Otherwise, if we try and do, 0 minus 0, what are we going to get? 0, which is what we're looking for, but that's a false positive. And if it wasn't 0, it could be any other number. We subtract it by itself or subtract it from itself, we're going to get 0. So we have to stop there. And that's why we have while left is less than right rather than less than or equal to right. So we have to have that. That's our failsafe, and that means that we're done. And we could explicitly return undefined at the end, but this works fine too. Yep, so that is using 2 pointers, in this case working from the far left side and the far right side towards the middle. That's not the only way of doing it. Next, I'll show you a problem where we actually start from the same side and just look ahead rather than going from the left and the right simultaneously. We just have 2 pointers on the left side. That's next.